Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over how you can find the empirical formula of a substance using just liters of the products that are formed from this particular reaction. So let's get into this. So in this case, normally when you do a combustion reaction problem, they give you mass of the different substances, and then you convert the mass to moles, and then you get your mole ratio of your pseudo equation and so on. In this problem, they're using gases and they're giving you liters of gases. So in this case, you kind of have to use your gas laws to help you figure out the number of moles that's involved in this particular problem, in this combustion reaction. So let's go ahead and get into this. So we have a 1.0 liter sample of a gaseous compound of hydrogen, carbon, and nitrogen, gave upon combustion 2.0 liters of carbon dioxide, 3.5 liters of water vapor, and 0.50 liters of nitrogen. So with all the gas volumes measured at the same temperature and pressure, that's going to be important. And then they ask, what is the empirical formula for the compound? So whenever you're trying to find the empirical formula through a combustion reaction, they're going to give you the amounts of products, and then your first step is to get the amounts that they give you of the products and convert it to moles in any way you can. So, but in this case, they gave us liters. So what we're going to need to do is we're going to have to get liters into moles somehow. And so that's where the gas laws come in. So it's really important that they told us that all the gases are measured in the same temperature and pressure. Why is that important? Well, let's go ahead and do our gas law. I'm gonna show this by using the combined gas law. So if I do the combined gas law, that's going to be P1 V1 over T1 N1. And that's going to be equal to P2 V2 over T2 N2. And so you can use this equation to determine what your amounts are based on changes in the different kinds of properties. So we have pressure, volume, temperature. So if you change one set of properties, then that's going to lead to another set of properties. Okay, so in this case, they're telling us that the temperature and pressure are constant, right? So all of this is measured at the same temperature, same pressure. So the temperature and pressure are not changing. That's important because anything that's kept constant or is not changing is eliminated from this equation. And then what's left over is the equation that we can use for our gas law problem. So here, they're telling us volume or pressure, is constant. So I'm going to eliminate temperature from the equation. They're also telling me pressure is constant. So I'm going to eliminate that from the equation. And what we're left with is V1 over N1 is equal to V2 over N2. And so here is the equation that we could use for this particular problem. Now, we're not going to use this equation to solve the problem, but this equation clarifies something for us, or brings to light something that's going to be very helpful. Notice that if I change the volume, right? So if I start with volume 1 and a certain amount of a gas 1, notice that the change in these are directly related to it. This is a direct proportionality here. So if I was to double the amount of gas I have, right, then I would have to double the amount of the gas, right? So let me put it this way. Notice that the ratio of the volume and the amount of gas that I start with is equal to the ratio of the volume and the amount of gas that I end with. So whatever I do to the volume, the same thing has to be done to the amount of gas in order to keep the ratio the same. So if I double the amount of the volume, then I would have to double the amount of the gas. If I double the amount of the gas, then the volume is going to double. If I cut the amount of gas in half, then the volume is going to be cut in half. So this is a direct relationship. And why is that important? Because it shows us that the volume change is proportional to the amount of gas that's changed, right? So basically what that means is that volume is going to be proportional to the amount of gas in moles. Well, why is that important and insightful? Well, notice that they gave us liters of the gases. They didn't give us moles, right? Right? So, or they didn't give us masses of the substances. Normally, in a combustion reaction where you're asked to find the empirical formula, they're usually giving you grams, or maybe they're giving you a percent composition that then you convert to grams, which then you use the molar mass to convert to moles, which is what we want. We can't do that in this problem because we're not given mass, we're not given a percent, we're given liters. But because volume and the amount of gas is proportional, we can treat the liters, the volumes that they're giving us, as moles because volume and the amount of gas are directly proportional to each other. So let's go ahead and do that. So let us treat the volumes as if they're moles. So we have 2.0 liters carbon dioxide, right? We can say, well, let's treat that as 2.0 moles of carbon dioxide. Okay? And so we can then convert this to moles of the carbon. Now that we have moles, right, the idea would be to convert moles of our product to moles of the element that we're interested in. So remember, our compound is made up of hydrogen, carbon, and nitrogen, right? So all of the carbon and carbon dioxide came from the carbon in our substance. So we're interested in the moles of carbon, not carbon dioxide. So we can use the mole ratio in the formula to convert to moles of carbon. So for every one molecule of CO2, we get one atom of carbon. That's a ratio of 1 to 1. That's the same as the mole ratio, right? So 1 mole of carbon dioxide will give me 1 mole of carbon atoms. So then I use that. So 1 mole of CO2 on the bottom, 1 mole of carbon on top. Moles of carbon dioxide cancel out. And of course, I end up with 2.0 moles of carbon. And I do the same thing for water vapor, right? So 3.5 liters of water vapor, that's going to be the same. We can treat that as 3.5 moles of water vapor. Put that over 1. And notice that all the hydrogen that reacted in our compound that we're interested in is ended up in the water. So we're going to convert moles of water to moles of hydrogen, and it's a 1 to 2 ratio. So for every 1 molecule of water, I get 2 atoms of hydrogen. So the same thing, 1 mole of water is going to give me 2 moles of hydrogen atoms. So I'm going to use that ratio. So I'm going to put 1 mole of H2O on the bottom, 2 moles of hydrogen on top, moles of water cancel out, and now I just multiply by 2. 3.5 times 2 is 7.0 moles of hydrogen. And finally, I got nitrogen here, so I have nitrogen gas, N2. So they're giving me 0.50 liters of N2. Again, that's going to be the same thing as 0.50 moles of N2. Now notice that I have moles of N2, which are molecules, but I want the atoms. So every 1 mole of N2 is going to give me 2 moles of nitrogen atoms. So I'm going to use that as a conversion. So 1 mole of N2 on the bottom, 2 moles of N on top. Moles of N2 are going to cancel out, and then I multiply a half times 2 gives me 1.0 moles of nitrogen. And again, just to clarify, the reason that I am converting this to atoms and not keeping it in the molecules is because my original sample has atoms in it, not molecules in it. So it's a certain number, it's a certain moles of hydrogen atoms, it's a certain number of carbon atoms, and it's a certain number of nitrogen atoms, not nitrogen molecules. Okay, now I have the moles here. Now all I need to do is write the moles as subscripts because we're trying to find the empirical formula, and the whole reason why we got our elements in moles is because the empirical formula is a mole ratio. The subscripts are the ratio of moles. So since we have our elements in moles, these are the subscripts. So we're going to write our formula with those subscripts. So we have C, carbon, so that's 2. And we have H, that's going to be 7. And then we have N1. And then normally you would divide each of these by the smallest number in order to get one of the subscripts to be 1. But since we already have 1 as the lowest number, or the lowest whole number number for our subscripts, we don't need to divide by 1, or we don't need to divide by the smallest. The smallest here is 1. We end up with the same number, and all of these are whole numbers, so we don't have to multiply to get them into whole numbers. So we're done. This is the empirical formula for this substance. And that's how you do it, ladies and gentlemen. So anytime you are given the amounts of your compounds of a combustion reaction in terms of liters of gases, right, and you're asked to find the empirical formula of the substance, check to make sure if they gave you the temperature and the pressure in constant. Now, if it's not constant, they would have to give you the temperature and pressure, so that way you could use the ideal gas law to then convert the liters of the various compounds or products into moles. And then once you got that, then you just convert to the moles of the different atoms, right? But in this case, since they told us that it was same temperature, same pressure, the temperature and pressure is constant, we can avoid doing that extra calculation because we know that the volume in liters is going to be directly proportional to the moles, so we can treat them the same. That's it for this video. I hope you enjoyed this video. If this was insightful, if you enjoyed this video, if you loved this video, if you learned anything from this video, Please like the video, share the video, hit that like button somewhere over there. Also, make sure you subscribe to my channel. It will help me out. Also, make sure that you click that notification bell. When you do that, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with, put it down below. If you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.